Hey class, this is a little help session on Lab 7, which is Forces in Mass Movement, otherwise called Landslide Hazard. For this lab, these are the different things that you'll need. If you don't have them, make sure that you borrow them from somebody, or you can even do them by printing them. So you can literally print out a protractor and a ruler from the internet. The ruler must be in millimeters, just so you know, for exact measurements. Or you can even do everything through some sort of online tool, or not even online, just tool. Like I use PowerPoint and most of the things work just fine. So yeah, but ideally and for easier ways to do this is that you actually have these 4 different things: ruler, protractor, calculator, and a printer. Okay? Alright, so the beginning part of this, I'm gonna skip through. It is a little bit of a help session in terms of understanding vectors. So it's a little bit mathy, but not too much, I suppose. So I'll let you go ahead and do the first 2 or 3 questions on your own. So make sure you pause the video, read through this beginning part, and understand vectors. I do want to point out one thing here before I continue onward. Here it is said that 2 vectors are equal if they have the same magnitude and direction, regardless of whether they have the same starting point. So, as you can see, A and B in this case are the same length, so the same magnitude, and they have the same direction. So they are the same vector, basically, okay? They're equal. So that is an important fact that we'll use in the coming questions. Okay, so go ahead and read through all of these bit and continue onward to question 3. Okay, so hopefully you got those done. So what is the length of the vector that must be added to vector A to get vector C in the image below? So ideally, if you have read through the other stuff, what you would do is you would place the beginning part of the vector, this beginning part of it, either here at this end or here at this end, and then the ending part at either here this end or here this end. And then that would be the direction of the vector, either this way or this way, and then the magnitude would be the length from this end to the other end. Nothing too crazy about that. You're going to go ahead and have to measure it on your own in order to complete the question fully. Alright, second part. This one I will take you through a little bit in more detail. So, when dealing with landslides, we are interested in the interplay between 2 forces. Those forces being friction, which works against objects moving downslope, and the pull of gravity downslope, otherwise called GD. So basically, from this picture that you have right here, GD pulls the house that way. So G stands for gravity and D for downslope. And then the friction force, which works against those objects moving downslope, works opposite. So friction, you can imagine as an arrow pointing upwards here on the slope. Okay, so to find the gravity downslope, we must resolve the gravitational force, otherwise called just G, which, as you see, goes completely down. It's, you know, like gravity, it goes towards the core of the Earth. And it's resolved into 2 different components. One of those components is going to be perpendicular to the slope, so this one right here, and we call it GP, so it stands for gravity perpendicular, and the other part is going to be the gravity downslope. So gravity itself, it's resolved into 2 different forces, if you would, gravity perpendicular and gravity downslope, okay, into two of those which are components. So that idea again is portrayed here. What they're saying basically is that if you want to find G, G is made up from GP and GD. So if you were to place, for example, GD all the way down here, that would be an equal vector. So let me show you that in the other program. 1 second. Okay, so this is that same image that we have in the PDF file, but I'm going to show you how the GD and GP vector components make up the gravity itself component. So here they have them broken up like this, so that you can easily see that this is the gravity that is pulling the objects down slope, and this is the gravity that is perpendicular to that slope, right? But what we're going to do is that we're going to make an equal vector for each of those. So remember, equal vectors must be the same magnitude and the same direction. So that will be the vector that is equivalent to GD, and this will be the equal vector that is equivalent to GP, right? Pretty much, maybe this is a little shorter. Okay, so if we put this equivalent vector of GP here, well, in theory this should work. Oh, it's a little short in this way. It will complete that triangle just like they did in the summations for the previous exercises on vectors, on questions 3 and 4, I believe. And if you do the same thing with this equivalent vector to GD, you'll see that it also completes it. So from my measurement, it's not perfect. This is just a cartoon, so it's not going to be absolutely perfect, but the idea is that, you know, they match pretty much exactly. So you get what that means, hopefully, by me doing that little demonstration. All right, so now from the image in the next page, so that's going to be this image right here, you have a few questions that you need to answer. The first question is, which of the following diagrams of houses on slopes is stable? And by stable, I mean that the forces that are pulling the objects downslope are less than the forces that are working against those objects moving downslope. In other words, saying that the friction force is greater than the gravity downslope force. Okay? Then, which of the following diagrams of houses on slopes is unstable? So here it explains that where unstable means the worst case scenario for the house. So again, that would mean that the house actually tumbles downward. So if you think about this diagram, in order for the house to actually go downward from this position, the gravity downslope force must be greater than the friction force that is resisting the house from going downslope. Great. And then it also asks you which of the following diagrams of houses on slopes is just about to slide. So by just about to slide, I mean that if you add a tiny bit more gravity downslope force, then that house will topple over. It will fall downhill. So just about to slide would mean that the friction force that is resisting the house, that is making the house resist falling, is the same length as the gravitational force downslope. Okay? So hopefully, by looking at these 3 images, you will see that they have different, or the gravity downslope vector is the same for all 3 of them, but that the friction vector is different for all 3. So in one case, the friction vector will be the same length as the gravity downslope. In one case, the friction vector will be less, smaller, and then the other case, it will be longer. So you'll be able to answer this question and then 4 and 5 as well, which are actually on your quiz. Alright, so next up. On the following diagram, so these ones right here, resolve the gravitational force G, which is shown to you in all 3 of those diagrams, into a downslope force and a perpendicular force. So those are the 2 components of gravity. Okay. So in the first example, this one right here, the dashed lines here and here show the direction of the gravity downslope force and the gravity perpendicular forces. You just need to draw the 2 vectors so they add up to G, just like we did in the previous image. In other words, you will need to make sure the directions and lengths are correct. And please label the vectors as you draw them. So what they want you to do is go ahead and draw basically this graph with how we had it before, with the GD here or the GP here, either way, and make sure that you measure all 3 components. So the gravity, measure how long that is, and measure how long the gravity perpendicular is and the gravity downslope is. So I'll show you how to do the first one, and then you guys will be able to do the other 2. Okay, so these are again those same three images. Let's start with drawing the vectors for the GD and the GP vectors that are from the first image. So the dashed lines already give you the directions of where those should lie. The dashed lines are going to differ for cases B and C. Remember, GP is always going to be perpendicular to the slope. That means it's going to be at 90 degrees from the slope. So in this case, it's going to point like this way. And in this case, it's going to point more towards the left since that slope is more inclined. Okay? But in this case, for number A, they gave us the actual direction, so that should be easier. So let's place the GP first. Let's see, so it starts there and it has to go till somewhere around there. And then the GD, and we'll accommodate this. We'll start there and go till somewhere around there. So the exact measurements of how long they should be are going to be known to you by making a right angle between them. So what I mean by that is you're going to have you can use your ruler for this. In my case, I'm going to have a box, oh, that was silly, that I'm going to position. I'm going to position my box here perpendicular, lying on the slope, and having it extend all the way till I match my G. Perfect. All right, and now we need to make two vectors, one that is equivalent to GP, and place it on our box basically. And it's pretty much the right length. A tiny bit, should be a tiny bit smaller, but not much more. Okay, so that is going to be actually how long GP is. So I'm going to erase this one, and I'm going to copy this one. And that's going to be our new GP, a new and improved and actually correct GP. Excellent. And then we're going to make one for GD that actually matches the place where it should fall. So again, that's going to be how actually long GD should be. So I'm going to erase this GD that we had made and place our new and improved GD up there. Okay. Excellent. Great. So now that we actually have the right measurement for those two components of G, we can actually, with your ruler, you can measure the length of them. Okay, so if I were you, I would go ahead and finish the other two cases before I go ahead and continue onward, but it's your call. And it doesn't seem like it's useful what you just did, but it will come useful as you answer these questions. So let's go ahead and follow through. So the G vectors, so all these three that are in the pictures, are all the same length, which is 34 millimeters, okay? If each of these houses, I should say, weigh 34,000 pounds, then each millimeter of length of the vector in this diagram equals how many pounds? Okay, so hopefully you're thinking that there's an equivalence in between how much weight there is being supported on the slope and the amount of, or the magnitude, I should say, of the gravity vector. So hopefully you will answer this respectively, and it's pretty straightforward, so I don't think you will go wrong. And then next is, how long would the G vector be if the house was 60,000 pounds? So now that you know that there's an equivalency here, you'll be able to, I think, also find out what that G vector would be if the house actually weighs 60,000 pounds instead of 34,000. Okay, so now number 6, measure the gravitational downslope component in each case of the diagram above. So once you have finished those 3 cases, measure the length of the GD. How many pounds of force are pulling the house downhill in each case? So in this case, I'm not asking you the length of it in millimeters, but I'm asking you in pounds. So here is where this equivalency becomes important so that you can answer all of these questions appropriately.